How's it going, everybody? So last video was pretty involved. It was about a 2 hour, 45-minute marathon through basically real complex analysis, and we even touched a little bit on stochastic analysis as well with filtration, sigma algebras, Lebesgue theory. We really did quite a bit. And just to review, remember we had complex differentiation, talked a little bit about topology, and from the epsilon delta definition of the limit to resolve Zeno's paradox, and then again that measure theoretic foundation of probability, which is a really good setup for stochastic processes. But essentially, what we really did, if you take away anything from that video, is that we built a complex engine that was capable of describing continuous change, and essentially that was very although it was really long and took a lot of work to do that, and it's a lot of it, the intensity of the concepts were very dense. It wasn't exactly, there was still a grounding in like what we were doing, okay, conceptually. But there's really a flaw though in everything, which is that if you wanted to find a derivative in the real number line, for some n dimensions, or calculate, maybe a path integral or something, I don't know, we implicitly assumed that the existence of a standard basis is like just a thing. We assumed a grid, and we wrote vectors as columns of numbers, so just like x, y, z and stuff. And of course that's a lie about the physical universe, okay, because space and the world doesn't come with a grid attached to it, right? If you're a photon, you're going through the void, you really don't care about which way x or y is, in terms of the coordinates. Now maybe if you're a neutrino, that's a little bit, I don't know, that's a little debatable, but essentially for the case of just common sense, right? If I tilt my head, my brother throws a football, right, and I'm like, oh, I'm gonna tilt my head a little bit, the football's trajectory shouldn't change in the physical world just because I'm looking at it a different way, okay? So that's the essence of this chapter. And if our physical laws depend on the coordinate systems we choose, right, if the football starts to move like in a different way because I'm looking at it differently because of the coordinate system I'm choosing, then that's not a law of nature, right? Those are artifacts of your perspective. So welcome to the idea of invariance, okay? And philosophically, what this means is that we're trying to study truths that remain true regardless of how you measure them. And we're stripping away coordinates essentially to build something called linear algebra by defining vector spaces and duals. And then we'll talk about linear operators, and basically if there was a fundamental theorem of linear algebra, the spectral theorem, basically. And we'll talk about that today. So a little bit less intense than last time, but conceptually much harder. So this is probably going to be the hardest video that I made yet, to understand, and it takes a little bit of mathematical maturity to get through this, okay? But again, we learned how to measure things in chapter 1, right? We learned how to measure, but in chapter 2, we're going to learn what exactly we are measuring. So let's get rid of this idea of a grid, all right? And we're going to begin first by destroying columns of numbers, right? Because again, we mastered limits, derivatives, integrals, probably, whatever. We've rigorously defined these things on real numbers with the aid of coordinates, but every single theorem that we have used depended on a fixed basis and origin, okay? But the real world depends or admits no coordinate system. So if I rotate things or boost them or transform them, or we will render every single coordinate dependent statement a little bit questionable, right? So again, a vector now, this idea of a vector, probably heard this thrown around a little bit, just column of numbers, works, right? But vectors are not the numbers, okay? They're not just some, you're basically taught in high school that a vector is like a list of 3 numbers in 3D space, but The numbers, again, are not the vectors. Those numbers are the shadow of the vector cast on a specific coordinate system. And we need a definition that captures the object of the vector itself, not the shadow. And so hence we're going to first define something called a vector space. All right, and you might see all of these axioms and like exactly, okay, what is a vector, right? Okay, we're saying a vector space is over a field, and the field in general is typically the complex or real numbers. It's equipped with two operations. So, we have the product of the vector space with itself mapping onto the vector space. All right, is in this abstract way preserving addition and scalar multiplication. So if I take the product of the field and the vector space, mapping this onto the vector itself, this would give us scalar multiplication. Okay, so the multiplication depends on the field that we have. Now, all right, and then here's these 8 axioms. So let's go through these. The associativity, commutativity is pretty standard. This one's important. So there exists some zero vector. Okay, so something inside of a vector space, right, that if you add it, you will get the vector again for itself for all of the vectors. This is called an additive identity. All right, and we can also distribute scalars, distribute the scalars onto the vector like this. Associativity, again, we can choose how we multiply. If we want to multiply the two scalars together and then multiply it on the vector, or we can just multiply the scalar within the vector and then multiply the scalar after doing that. Okay. Also, the multiplicative identity, that means that there exists some, like one thing. When I multiply it, it's going to give me the vector back. All right. Again, we also need to define a subspace or a subset. Sorry. Oh, a subspace. A subspace is a subset of the vector field if it is closed under addition of scalar multiplication. So that basically means that there's some way, or really, it just means that if for all vectors that exist, or for all vectors, there exists some negative version of that vector that if I add them both together, it'll give me the null vector. Okay. All right, that's what a subspace is. In other words, is if I have a subset of the vector space. Okay, and it's closed. All right. Now, a way to think about this is, in simple terms, is a vector space is a set of objects that you can add together and scale by a number. That's it. Of course, it satisfies all these 8 axioms, but nowhere in those axioms do we mention coordinates or matrices. All right, that's the first thing you need to understand. And this abstraction allows us to treat strange things as vectors. So functions are vectors, polynomials are vectors, quantum states, if you will, are vectors. As long as you can add those states to get a superposition and scale a state by a complex number, then it is a vector space, fundamentally. All right, now that even though we hate coordinates, we sometimes need them to compute things. So this brings us to the basis. So first, let's define something called linear combination. This just means if I have some coefficients in front of my vectors that are scaling my vectors, if I add them all up, if I add them all up, that's a linear combination. Span is if I have the set of all possible linear combinations of a set, that is denoted as the span of the set. Okay. Linear independence is another one. So let's say I have a set of vectors. It is linearly independent if the only solution to this, which means that if I add the vectors to themselves, right, or add the vectors times some arbitrary scaling factor, that if it equals 0, the only solution to this is just multiplying everything by 0, essentially. All the scalars must be 0. And that's the only solution, the trivial solution. That's what it's called. So think about this, like if I have, 2 vectors and I scale them in a certain way, and there's such a way that I can add them but I'll never be able, or that I can add them and get 0 from them, they're on the same line. Okay? And you can think about that and verify that in your head for yourself. But if I have 2 vectors, right, that I can add, or more vectors, right, that I can add together, and then they sum up to be 0, they're on the same line, okay? Linear independent, so they would be called linearly dependent vectors. Linear independence tells me if I have a bunch of vectors, there's no possible way that I can add them or subtract them such that they give me a zero vector. So that's what that means, okay? Verify that in your head or draw that out, whatever you need to do to understand that. But really, now that the basis then is a set of vectors that is linearly independent, and we're going to inherit this definition here, which is that it spans the vector space, okay? So a basis, again, is a set that is linearly independent and spans a vector space. The dimension of the basis, right? This is a subtle part, but how do we know that every basis has the same number of elements? And how do we know dimension is a real thing and not just some choice, right? So the first theorem to use is that all bases of a vector space have the same cardinality, and this depends on the Stein's exchange formula or lemma. So let's say if I have a collection, well, let's say if I have a set of vectors here, v, and another set of vectors, w, and there's a different number of them, m and n, we would say v is linearly independent. And let's say w spans the whole vector space. Then m is less than or equal to n. Furthermore, you can basically swap the m's and the w's to form a new basis. So that's another kind of like lemma. And to prove that, really, it says, okay, to put this into perspective, right? If you have a set of linearly independent vectors and a set of spanning vectors, you can swap them out one by one, and this is a proof that the dimension, essentially, this is a proof that the dimension is an intrinsic invariant of the space, okay? I didn't write this down, but that's kind of what the whole chapter is about, right? Invariance, right? So this is our first invariant that we have. The dimension, essentially, that is invariant from the set of independent vectors and the set of spanning vectors, okay, of that vector space. So whether you use Cartesian coordinates or spherical harmonics or whatever, Fourier modes or number of degrees of freedom, okay, again, the degrees of freedom that you are constricted to is invariant. So for example, hopefully this makes sense, but if I have R3, right, a standard basis to span the entire three-dimensional space of real numbers would just be 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the basis then would be the set E1, comma E2, comma E3. Of course, there's three things in that set, so it has a dimension of 3. Well, look at the polynomials. And if we look at polynomial vectors, or a basis that spans the polynomials, we'd have 1 t squared. There's three things in it, and so we would note that these two spaces are something that we call isomorphic. Isomorphic just means it has the same exact structure despite different elements. Okay? And this is our first little hint of category theory. Okay, but this will be the last chapter we're going to talk about category theory. Okay. Great. Now let's define functions, okay? But we need to essentially define functions where we can take a linear vector space and map it onto another vector space. And what this will do is preserve a structure, which is just addition and scaling, right? But instead you can put the function acting on the vectors themselves, right? And just kind of move the scalar out of the way. Same thing, right? But we'd call this a linear map, okay, in general, if we're mapping a space onto another space. Now, there's some key subspaces. When we study this with matrices, especially in the last episode, we talked about columns, right? Because what is the derivative? The derivative is a linear map, right? But let's look closer and study this a little bit more. Because now that we have this idea of a dimension of a vector space, right? Columns, determinants, but without coordinates, we can now talk about subspaces. So this first thing called the kernel, and it looks like ker t, right? This is the null space. This is something called the null space. Why do we call it the null space? Because it's everything that this linear map will crush, or it's the set of everything within the vector space. That whenever we do a linear map on the vector, everything that's zero. So it's everything that crushes, that t crushes to zero in that vector space, and it measures essentially the loss of information. And the loss of information is the null space of the function. All right, or it's a subspace from this linear map. The next one is the image or the range. It's essentially everything else, like everything that t can reach within the vector space. Okay. Now, this leads to something called the rank nullity theorem, which essentially is a conservation law for information. So let's say I have the dimension of the null space, or dimension of the kernel, plus the dimension of the image of t. If I add both of those together, it would give me the dimension of the total vector space. And here's the proof. You can kind of read through it, but think about it physically, okay? I think it's more important to think about it physically. The dimension of the input, v, must go somewhere. Either it survives the output, right? Or it gets crushed to zero, right? The output will get crushed to a zero, and that's called a kernel, and you cannot destroy dimension without a trace, right? So that's essentially really what the proof allows you to show, which is that if you count again the dimensions again, remember the k and then the n minus 1 dimensions that come from these extra vectors that are not included within the basis for the kernel, right? These things that we've lost. The total dimension of the vector space should be conserved. Okay, it's an invariant. In other words, we're just confirming again that dimension of a subspace is an invariant. All right, let's look at the first isomorphism theorem. So what this allows us to do is quotient or divide spaces by each other. All right. So in order to do this, elements are something we call cosets. Okay, so this would be some vector that's within the original vector space plus some u, right, that we can divide out, the subspace. And in order to do that, we would just say v plus u plus w plus u. You can simplify that as v plus w plus the subspace, right? Because it's just kind of how we're going to modulo it out. And then there's also the scalar, that if we use the scalar on the vectors, you again, it follows the same rules, but again, u is a subset, it's a coset, right? So we have the set of vectors and then another set, a subspace. The dimension of the quotient space would then just be the dimension of the vector space minus the dimension of the subspace. And here's the theorem: if we have the vector space modulated out by the kernel of some function acting on that map, or some linear map, is isomorphic to the image of the map, all right? Via essentially using the properties up here, right? It just creates this map. What this means is if you collapse the kernel to a single point, okay, the map becomes an isomorphism onto its image, okay? Another thing that you can keep in mind is that we can actually transform between different bases. We have to define something called a transition matrix, but this is really important because if I have B, right? If I have B and then B prime, and they're both equally and rightfully bases of the vector space, we can define a matrix that has columns of coordinates B prime and vectors in B, all right? And the matrix T, right, the matrix of the linear map, will, with respect to the other basis, the transformed basis, with respect to B prime, the original basis that we're in would be the inverse of the transition matrix. Remember, the transition matrix has columns as coordinates of B prime and vectors in B, okay? So we'll take the inverse of that matrix, right? And then, of of course, this is the linear map in the basis. Remember, the map itself is basis dependent, so within the basis of that we're in, and then again act on that other matrix, and this will allow us to change bases. All right. Now, we're going to arrive at really probably the most important concept for physics. And mathematicians usually get this a little bit better than the physicists do, especially in quantum mechanics and like learning bracket notation. We really don't have a rigorous, reasoning or really proof or explanation for dual spaces. But it's also really confusing for physics people, but math people are fine. Okay, so it's very important. The dual space, and it's denoted V star. Is associated with a vector space. So if V is the space of states, okay, so we could say like position or some, I guess, quantum wave functions, right? If we have things in that vector space, what is V star? V star is a space of linear functionals, okay? And you can think about them as linear maps that eat a vector and spit out a scalar number, okay? So, for example, here's an evaluation pairing. So if I pair, some linear map with the vector, it's going to spit out the scalar. In other words, we're going to go, it's a set of all linear maps from V to the field of scalars that is the vector space is respecting, okay? Particularly in the multiplication sense, okay? So why do we care though? So if phi, right? Again, this function phi of V, right? What this is it's a map of V onto F, right? A map of V onto F. Why do we care about this map? Because it is something that we call a measurement, okay? This is inherently what we call in quantum mechanics the bra, okay? The bra and the ket. And I'm sorry for being really physics heavy. I know this is mostly a math video, but this is really important because the ket is the state of the system, all right? This was motivated in a physical way in the development of this mathematics, right? The ket is the state of the system. Again, that's the V, that's the vector. But the bra is the device that's measuring the system, okay? So measuring the system, the state of the system, and the measurement is a function of the state. See what I'm saying? So when you put them together, this device here will act on the state and give you a number, and typically, this gives you like a probability of the amplitude or something, all right? Geometrically, a vector V is an arrow, right? But a vector V star is not an arrow, okay? It is a set of what we call parallel level sets, or like, contours where a function is equal, okay, in general. So the length of the dual vector is the density of these level sets or these planes, right? Is the value of the measurement. The value of the measurement is simply how many planes the arrow, or the vector arrow, pierces, okay? And really, I would encourage you to go look up what I'm talking about. The length of, I know this isn't written, but the length of the vector piercing certain planes of your dual space, okay? You should look that up, okay? Just try to find something, like understand what I'm talking about. But the distinction, again, between the arrow and the layers is the difference between contravariant and covariant vectors in general relativity. All right, okay, that's enough physics. The dual basis, then, let's say we have, the set of E sub I, right? So just for, a basis for the function, the dual basis, or given a basis for the vector space, there exists a unique there's a unique dual basis, and we'll say epsilon to the j, super j, okay, superscript j, for the dual space that's defined by the Kronecker delta. Okay, so this means that if I have the dual basis, the unique dual basis acting on the original basis in that vector space, we can define this as delta sub I superscript j. If I is equal to j, this gives us 1. Okay, if I is not equal to j, this gives us 0. But this basically defines the mechanics of orthogonality, or not just orthogonality, but essentially the assignment of scalars to basis vectors extends uniquely to a linear functional. So this guarantees that the dimensions of the dual space is equal to the dimensions of the original vector space. All right, and you can prove this in such a way where if you have a function of everything that we're putting in of the basis vectors with some coefficients, this will give us a new sum. Okay, where a is assigned to so each a basis in that dual space is assigned to e. All right, and keep in mind, again, this is a scalar. This becomes a scalar. All right, the linearity is clear, and it is unique because they have to agree on the basis, right? So that's essentially why the Kronecker delta is defined in such a way. So let's say we have a vector space that belongs to the set of real numbers and in dimensions. Then the dual space is the space of row vectors, and the action, okay, or the measurement of those vectors is a matrix multiplication. So it'd be row times column, all right? And then with row vector times column vectors, or just more generally, let's just say we have some phi and psi, right? Okay, our measurement and our state in the dual basis, or in the dual space. And if they're linearly independent, that means that the dimension of the v of the original vector space is greater than or equal to 2. We can construct v with phi of v to equal 1 and phi of v to equal 0. And if we let this collection for our basis with a function for each vector that's in the basis to be equal to 1, phi of e to j is equal to 0 for j is greater than 1. And you can adjust then for the state. Okay? And this is very interesting because we can explicitly let the set of, oh my gosh, I keep clicking on this. We can explicitly let the set of the measurement map, right? And the states and some eta sub 3 be a basis of the subspace. And then define v in terms of eta and v to be, again, the Kronecker delta for eta and phi, because this works if we have, again, the measurement acting on v to be equal to 1 and the state acting on v to be equal to 0. All right? So that's kind of a lot. But again, you can think again, the length of that dual vector is the density of the planes that are really defined by those level sets, right? Because again, in the dual space, a vector is not an arrow, okay? They're rows. All right. The double dual and reflexivity. So this motivates a deeper question, which is the vector space the same as the dual space? Of course, they're not, but if V is finite dimensional, they have the same dimension. So technically, they are isomorphic, right? You can map one onto the other, but to do it, you have to pick a basis, okay? So remember the vector, let's just think about a vector, I don't know, in general, like 1, 0, 0, right? And it maps to a functional 1, 0, 0, right? And rows instead of columns. If you change your basis, that map changes, right? So that really shows you that it's they're not isomorphic. Or I mean, they are isomorphic, But this isomorphism is kind of unnatural because it depends on your choice of basis vector. Hopefully I didn't lose you in that, but okay. This explains why we have essentially the double dual, okay? Because what this allows us to do is find the dual vector space of the dual vector space, okay? And this is the space that will eat functionals, all right? So we don't have to choose anymore arbitrary bases, and this becomes a natural isomorphism or a natural embedding, right? There exists a natural map J, right? So that we can take the vector space and map it onto the dual of its dual, or the double dual. And again, if you look at this equation closely, what is this? Okay, typically we think of the function phi. Remember, right? The dual space eating the variable v. But if we flip the perspective, we can say the variable v, right? The variable v, the vector within that vector space, is eating the function, okay, phi. And this map actually requires no basis, no coordinates, no choices, and it's intrinsically true. And because of this, the mathematician will often say the finite dimensional spaces are something called reflexive, okay? And the reason why they're reflexive is because the space looks in the mirror of duality and it sees itself. So, for example, right, let's look at an infinite dimensional counterexample. So if we say v is just the real numbers and they're polynomials, okay? V star contains evaluations at points, right? Limits at infinity or whatever. But v the v double dual is larger than v. So functionals on v star are not coming from polynomials. And so this in and of itself shows you that you can't use this for infinite dimensional spaces. But for finite dimensions, this J is an isomorphism reflexively. All right. But again, in the Hilbert spaces, it's not always true. Okay. So you have to make sure the dimension of the spaces are very important invariant, because it allows us to decide whether or not we can use the isomorphism of its double dual. All right. Now, let's also look at annihilators. Let's go over this briefly before we go to dual maps. But essentially, if we have a subspace, we'll coin this the annihilator. So u to the 0, or u superscript 0. If we have a subspace, which is a subspace of V, what happens is that the annihilator is a set of functionals that vanish on U. So if we look at the measurement of anything within U equal to 0 for all vectors in U, given this, and we want all the functionals, the function, the set of all linear maps within the dual space. If we take the set of that, there's a theorem that we can derive, which is that the dimension of this, again, is V minus the dimension of V minus the dimension of U. So if you choose a basis for U and extend it again with the V plus 1, so we're just taking everything in U and then extending it out for V to complete that full vector space. The dual basis can be defined as this. Then U, or U super 0, or the annihilating, or the annihilator, is spanned by epsilon plus 1 to epsilon in. And we can then have a theorem that the dual of the quotient space is isomorphic to the annihilator. All right. If we look at exact isomorphisms, we can say all of the linear maps in that dual of the quotient defines some phi of V, right? Which would be equal to V plus, again, that U, the vector space itself that is within the annihilator, and it's well defined again. So we can also take the converse as well. But yeah, I mean, this is important for geometry because in Euclidean space, the annihilator corresponds to the orthogonal complement. All right. And without a dot product, orthogonality does not exist, but annihilation does. Okay, that's kind of a little bit of a tangent, but I think that was a mathematical tool that's needs to be known or need to be covered. Finally, we need to ask though, how do the maps transform, right? So if we have a linear map, again, T that defines the vector space V mapping onto W, and if it's linear, and we also the dual map allows us to pull the measurements back, right? So let's say we have W star mapping onto V star, right? We can define this in such a way that, so again, we're pushing the vectors forward onto some space. We can also automatically we can have a dual map, which pulls the measurements backward. We can, again, define it as this kind of composition, or we can define them or they're equivalent to each other in terms of the the state composed with T and the dual map that pulls the measures back to T, or pulls the measures back measurements back to the state. And this is kind of the notation for the inner product, or the essentially the composition, right? Notice how the direction swaps though, right? T goes from V to W, T star goes from W star to V star. And if you write this in coordinates, the matrix for T star, the matrix for T star here is the transpose of the matrix for T. Okay? This explains kind of and again, you can walk through this, right? But essentially, if it has rows indexed by I and columns by J, the coefficient of e to the I will then swap the indices. And so you can verify this for yourself, but that's why row vectors transform inversely to column vectors. Now, this explains why in standard algebra, why do vectors transform with the inverse matrix of column vectors, right? It's because they live in the dual space. They are pulling back, right? They are pulling back against the flow of the map. Do you see what I'm saying? So here we pushed forward, but then we pulled it back, with the dual. So because the inverse vectors or the inverse matrix of the column vectors, and we have the transpose or whatever, they're pulling back against the flow of the map, and now we've really established the true skeleton here. If we want to look at a projection example, so let's again, an important thing to note is that only the zero vector and the vector spaces are invariant under every linear map, right? These are the only things that are invariant under every linear map. So if you have U as a proper non-zero subspace, extend the basis, define T 0 and complement, the identity U on U part is not whole of the vector space itself. So let's look at a projection as well. So let's say we have the square of a linear map. That would be equal to just the linear map, which implies that the vector space is the vector sum of the kernel of T, or the nullity of T, or the null space of T, and the image of T. All right, that's a very kind of nice projection example, and here's the proof. Okay, decomposition essentially is unique if you do a direct vector sum. Okay, those are important to understand, but essentially we now establish a nice skeleton. We have the vectors, states, and the duals, measurements, right, which is the space of all the linear maps. But so far, our operators are just abstract maps, okay? So in the next section, we will study operators on the space to itself and discover that discover the only numbers that survive the coordinate apocalypse, okay? The eigenvalues, all right? Because we're trying to get rid of coordinates entirely. And so that's going to happen in this next section. I need a drink because my throat is dry. So be right back. All right, so we're about 40 minutes into the video. Let's finish out linear algebra. So again, in the last section, we built the stage, we defined vector spaces, dual spaces. These are kind of like static structures that are waiting for something to happen, right? So let's let the actors arrive. If we look at a linear operator, this is a map of the vector space from the vector space to itself. And this represents, again, this is a map, right? So something's happening within the elements of these vector spaces that are, right, there's something happening, and it's like a dynamic process. So you can think of these as like rotations, or like stretches, or time steps, or evolutions. And the set of all such operators we'll call endomorphisms, or you could even think of like L of v comma v, whatever, right? There's different ways to form this, but it's an algebra, right? And you can add them. So let's say we have t, plus s, right? And we can scale the operators themselves, linear operators. But most importantly, we can compose them, right? So we can put act operators onto other operators. And the dimension of the endomorphism is the dimension of the vector space squared, right? All right. This sounds kind of cool, but a linear operator is just a map from space to itself. It represents a process, and if you're used to thinking coordinates, right, you probably think of an operator as like a square matrix, right? But here's the problem with that. A matrix is a liar. If you choose your basis, again, remember, if you tilt your head, rotate your point of view, the numbers in the matrix scramble completely. And a diagonal, matrix in one view might become a mess of a non-zero, entries in another, right? So we need to define invariance. And essentially, the central problem, right, is classification, right? We need to find the properties of the operator that refuse to change, no matter what coordinate system we use. And so what do? We need to define the most important invariant, which is called the spectrum, right? Imagine applying an operator to a vector, an operator that like rotates it, stretches it, or changes the direction of the vector. But sometimes you'll find a special vector, and when an operator hits it, the vector doesn't rotate at all. Actually, it just gets longer or shorter, and it stays on its own line. This is something we call an eigenvector, and that scaling vector is called an eigenvalue. So again, an eigenvalue is a scalar that's in the field, such that there exists some non-zero vector, where if we take the operator to act on the vector, or act on this particular eigenvector, it'll just give us a scalar that scaled the vector. So that's it. And we would define the eigenspace as the null space or the kernel of t of the operator, subtracting off the eigenvalues on the identity, right? This is just the subspace of all the vectors that are stretched by lambda. And again, so both of these things would equal to 0, essentially, right? Because it's the kernel of that space. So that's called the geometric multiplicity of lambda is the dimension, okay? It is the dimension of the eigenspace, right? The spectrum, then, we define, is just the set of all eigenvalues. All right? Why is this invariant? Because if you're sticking to your line, right? Sticking to your line is the geometric truth, and it doesn't depend on where you draw your y and x axes. So the set of all these eigenvalues, the spectrum, right? The spectrum is the fingerprint of an operator. So think about this again, to have like a physical analogy in quantum mechanics. These aren't just math, right? They're the energy levels of an atom. They're the only things you actually can measure. All right. So the question becomes then, how do we find these things without coordinates? How do we find the energy levels, or how do we find whatever the spectrum? And we look at something called a characteristic polynomial. Again, we got a hint from this from the eigenspace, but we look for the operator again with the operator t minus lambda I, where it fails to be invertible. And you can also get a coordinate-free definition. So the determinant, again, the determinant measures how an operator scales volume. So if an operator crushes a direction to 0, it flattens the volume, and the determinant will then be 0. So this is why we look for, essentially, the determinant, again, is the action on the volume form of a space, and this is known as the top exterior power. Since the top exterior power is one-dimensional, t acts on it by a scalar multiplication. That's the determinant. Okay, and so what does this allow us to do? Again, where it fails to be invertible, this leads us to the characteristic polynomial. Okay, so the Cayley-Hamilton theorem makes use of this characteristic polynomial, which is the determinant, again, of lambda I minus the operator. It says that every operator solves its own characteristic equation. So if you take that polynomial that defines the eigenvalues and plug the operator itself into it, you get 0. And this is the bridge that connects the algebra of simple numbers to the algebra of like these really complicated operators. So that means if you plug the matrix into the polynomial, you get a 0 matrix, and this gives you the scalar algebra of the field and the operator algebra of the endomorphism that structurally preserves the vector space. So there's the proof sketch. There's a linear polynomial called mt in sub t. It's called a monic polynomial, which is the smallest degree such that n sub t of t is equal to 0. What this does is it divides the characteristic polynomial. It shares the same roots, but potentially with some lower multiplicity. So instead of having like an eigenspace, right? That eigenspace, instead of being like a plane or like a hyperplane of eigenvalues, we can potentially reduce the multiplicities. But the structure of MT will tell us if the operator is diagonalizable. Multiplicities are the sizes of the largest Jordan blocks. Sounds pretty abstract, but it's just a structural thing about the matrix. So we have we have a theorem from this that a linear operator is diagonalizable if and only if the minimal polynomial m splits into distinct linear factors, so has no repeated roots like this, right? So if this characteristic polynomial happens, then it's not diagonalizable. Okay. Another way that you can equivalently say this is it's diagonalizable if and only if we take the direct sum over all the eigenvalues of the kernel of that, and that is equal to the vector space itself. And that essentially means if and only if the minimal polynomial is square free. All right, so that's the perfect way to put it all. Let's look at a rotation. So let's say we have the vector space of two-dimensional real numbers and some linear operator that's a rotation by 90 degrees. And a standard basis, which would just be 0, 1, and then 1, 0. Again, we would move everything from 0 to 1, and then from -1 to 0, right? That's how we're transforming it. The characteristic polynomial is the determinant, again, of this, so it would be the lambda, right, minus, these things. And if we take the determinant of this of the matrix that we construct here, which would then be, just lambda on the diagonals. I mean, pretty straightforward. You would get lambda squared plus 1, and the roots would be both imaginary. So over the real numbers, there's no eigenvalues. the spectrum is empty and there's rotation scales absolutely nothing in the real complex plane, or in the real plane. But over the complex numbers, however, two distinct eigenvalues, and the operator is diagonalizable. So again, in a perfect world, we could find a basis, right, be it entirely of eigenvectors. And this is again, that's what it means to diagonalize something. And in a basis where the operator acts independently on each dimension, you can uncouple, the mechanics of it, or like the physics. But the universe isn't always perfect, right? Sometimes an operator doesn't stretch space. It'll shear it and push vectors over, like a deck of cards or something. And when this happens, and we don't have enough eigenvectors to span the space, this is what we call the Jordan canonical form. This will represent the failure of diagonalization, right? It tells us that the operator has a nilpotent part. And sorry, this isn't right? The one, that's a one. The ones, right, sit on that nilpotent part. And this is a piece that eventually decays to zero if you apply it enough times, right? But there's a class of operators. There's a class of operators that will really, well, hold on. Let's first go through this. But you can look at the explicit computation of this. So let's say we have real numbers in 3 dimensions is our vector space, and here's our operator. If we take the characteristic polynomial of this operator, we get that the spectrum is just a set of, the eigenvalues. Over the minimal polynomial, it's not diagonalizable. Over the complex plane, it is. And if you row reduce it, you get the conjugate for that. So since the eigenvalues are distinct in the complex plane, the minimal polynomial is the same as the characteristic polynomial. There's no repeated roots. So the matrix is diagonalizable over the complex numbers, despite looking like a rotation block over the real numbers. Okay. But there is a class of operators that will never fail us at all. And we need to introduce something called the inner product. It is a way to essentially measure the angles between vectors. And we can also define something called the adjoint, okay? And so what the adjoint is, this is a coordinate-free version of something, again, the conjugate transpose that we talked about previously. And the transpose told us a lot about what we needed for the dual space, and why this was important as a method of going from the space of linear maps to the to the vectors themselves. So this brings us really to the entire climax of linear algebra. It says that essentially, but we can of course we can abstractly, by the inner product geometry, define the adjoint of an operator, and it just looks like this again. So there's a whole taxonomy of operators. So there's something called self-adjoint operators, which are Hermitian. That just means that the linear maps are equivalent to the original, or sorry, the adjoint operator is equal to the operator itself. So in basis, that linear operator is equal to the complex conjugate transpose of it. So in physics, these are like basically observables in quantum mechanics. So like the energy, momentum, and all this stuff. And this will always be real. Whatever you measure, whatever the eigenvalues are, they're always going to be real for self-adjoint or for Hermitian operators. Unitary operators mean they just satisfy this equality that if we take the map and the adjoint of the map, if we take the operator and the adjoint of the operator, we get the identity. And these conserve probability, amplitudes and time evolution. So again, these are constructed specifically for quantum mechanics. And linear algebra, I hate to say this, but linear algebra was created. Honestly, quantum mechanics is a class in linear algebra. That's all it is. Like I've taken a class in linear algebra, and I've taken a class in quantum mechanics, and we've done very little physics problems, if any. It's mostly just linear algebra. So the separation between linear algebra and quantum mechanics is none. There's none. Okay, that's all it is. All right. This might sound shocking to you, but if you take a linear algebra class like mathematics, linear algebra, there's a whole like laundering abstraction mechanism that's just not telling you that you're really doing quantum mechanics. Okay, there's no other thing that you're doing. Like there's no separation. All right, now that I'm done ranting. The normal operators, these typically don't get talked about in quantum mechanics, but it says that if an operator is normal, meaning that it commutes, again, with its own adjoint, it is perfect and it can be diagonalized. All right. So this is the parent class containing both self-adjoint and unitary operators. It's just slightly a little more general, a very slight generality. All right. Which means that if we can define, again, also projection for the taxonomy of these operators. The projection itself is equal to, if you take the square of the projection of the operator, they'll be equal to each other. That's an orthogonal projection, all right? Here's a theorem. Over the complex numbers, operators are normal if and only if they're diagonalizable by a unitary matrix, all right? If and only if t star is equal to t star acting on t. And you can try to prove this. This is a fun proof. And this uses sure triangulation commutator argument, another way to prove a rate with the coppers. Okay, now let's climax, guys. And I mean that in the least weirdest way possible. But this brings us to the entire climax of linear algebra, the spectral theorem, which says that if an operator is normal, meaning it commutes with its own adjoint, it is perfect and it can be diagonalized. All right, that's the spectral theorem. That's it. It's it's essentially quantum mechanics. So for physics, again, the most important case is a self-adjoint operator, right? These are, these are really, what's it called? The operators where t is equal to t star. And in quantum mechanics, these are, observables like energy, momentum, spin. But if you just go to a slight other level of abstraction, right, the spectral theorem, well, first of all, why is this a really important thing? It's because their eigenvalues are real numbers, right? So you can't measure imaginary energy, right? Doesn't really make sense. Also, their eigenvalues are orthogonal, all right? This explains really why quantum states are distinct as well. But before I get into that, the finite dimensional spectral theorem over the complex numbers. Assume t is a normal operator. It has an orthonormal basis consisting entirely of linear operators of t, or eigenvectors of the linear operators of t. It can be diagonalized by the unitary matrix. And the vector space is the vector sum. The direct sum over all the orthogonal eigenspaces themselves. All right. And so, yeah, and then the direct, if it's self-adjoint over the reals, that's what you get. All right. And there's a proof. It's actually a pretty simple proof. Let's look at angular momentum. What does it have to do with angular momentum? So let's say we have operators, right? J sub x, J sub y, and J sub z. These represent something called rotation generators. They satisfy this, where we have that they don't commute. This is just shorthand for like, oh my gosh, jx acting on jy, and then minus jy acting on jx, you'll get like an ih bar or whatever. They don't commute. However, if you take the square of the magnitude of the total angular momentum, oh sorry, just not the square of the magnitude, just the square of the total angular momentum, they commute. And because they commute and they're normal, they are simultaneously diagonalizable. So here's another one, commuting family theorem. So a commuting family of normal operators is simultaneously diagonalizable. This is another kind of nice corollary. This is why we label quantum states by simultaneous eigenvalues, j, m, are quantum numbers. Okay, quantum numbers is the same as just simultaneous eigenvalues. Example 4, which is the harmonic oscillator. So let's say we have an oscillator that's Hamiltonian. So the momentum squared divided by 2m plus, the square of the displacement. And we'll assume that it's on a Hilbert space, right? So for Banach space, where p is equal to 2, it is, which we covered in the previous episode, it is an unbounded self-adjoint, infinite dimensional, but its finite dimensional approximation in a truncated basis is self-adjoint matrix with positive real eigenvalues. Boom, you're chilling. All right, you can apply everything that we've used. We can apply linear algebra. Now let's look at functional calculus and polar decomposition. So let's say once we have the spectral theorem, we can really just treat operators like numbers, right? So if an operator is normal with spectral decomposition, like this, where P are projections onto those eigenspaces, we can then just define any continuous function f on the spectrum of the operator. Boom. So for example, we can just take the square root of the operator, or we can exponentiate the operator, or take the sign of the operator. For self-adjoint operators, the magnitude of it is just the square root of the square. All right. So, and also we can actually, guess what? Every complex number z can be written as a phase times the radius, right? That's pointing away from the complex plane. So every linear operator, invertible, can be written as some unitary rotation and the magnitude of t, where we have the positive self-adjoint stretch. So we take the dual of the operator and the operator itself and take the square root of that. And yeah. So in the same way, this is how we do a polar decomposition, but instead treat the operator as a function, as a number. Let's let the operator be invertible. So then u, the unitary rotation, would be the operator and the inverse times the magnitude of the inverse of the operator. All right. And the magnitude of the operator is the square root of t star and t. Okay. Another definition that you should be aware of is spectral radius. So, what is spectral radius? It's just the set or the maximum of the set of the given eigenvalues that are in the spectrum, right? And we take the limit as n goes to infinity, where we exponentiate the operator itself to the n, and take 1 over n of the norm of that, right? And that would be called the spectral radius, right? Just the maximum, given the magnitude of the eigenvalues, right? So, again, this explains, linear algebra explains why quantum states are distinct via the spectral theorem, and if you measure energy and get a specific value, you collapse the universe into a specific orthogonal subspace. And this algebraic structure guarantees the physical reality. Okay? Very amazing. I think this is really, honestly, I think linear algebra and quantum mechanics should just be taught together this way. I don't know why it's not. But, I think, petition this to your universities. Petition this idea. Combine physics and math, man. Because it's the same stuff. It's absolutely the same stuff. So, yeah. All right, so we've mastered single vectors. Cool. Linear algebra is over. But the physical world is built on interactions, right? So gravity, right, isn't just a vector, right? It's kind of a relationship between, matter and space-time, curvature, geometry, whatever the hell that is, right? Or flux, right? Magnetic flux. It's not like some line, right? It's a field that's passing through some surface, right? For the flux through a surface, right? To describe this, we need something called multilinear algebra, okay? And this describes the language of tensors. So a linear map eats one vector, right? A bilinear map eats two. All right, so it eats two different vectors. But dealing with bilinear maps is kind of clumsy. So ideally, right, we want to treat a bilinear map on V and W, these complicated relationships. We just want to turn this into a simple linear map, right? So we're going to do this with something called a tensor product, denoted as V tensored with W, right? Or V cross W tensor cross. I don't know what the name is for this, but you can think of, again, just a map, right? V sub 1, V sub k. We say it's k linear or multilinear. Just think, first of all, just think of the tensor product. Well, first of all, this is just, it would be the space of all such maps would be denoted as, L k of V given some field. Okay, so it depends on a field, right? And that's kind of the map itself. So we're just taking, again, the products of these vector spaces. Okay, so a tensor product, they're kind of this universal machine, right? It takes two separate spaces, V and W, and what it's going to do is it's going to fuse them into a single larger space. So it kind of traps the interaction between the two vector spaces inside the vectors themselves, and instead of just talking about a map that acts on V and W, we just talk about a linear map that acts on a single object, V tensored with W. Okay, just V tensored with W, and it simplifies the logic of interaction. All right, so again, it just converts bilinear problems into linear problems. So that's essentially what the whole idea of a tensor product is. The tensor product between vector spaces, on pairs, right, would enforce bilinearity. So again, it is the quotient of the free vector space, again, on those pairs. So it distributes accordingly. It obeys these particular laws. Scalars, do as you would expect. Basis and dimension. So a basis for V has a dimension m, and then let's say f sub j is a basis for W. Has a dimension of n. Then we would say the set, the tensor product of both of the bases is a basis for the tensor product space of V and W, and the dimension is just, as you would guess, m times n, right? And for pure vector or for pure tensors, okay, the elements or tensors themselves are objects that have elements of the form of V tensored with W. Okay, so it's just two vector spaces, right, that are just tensored with each other. For general tensors, you would just take the tensor product of their basis vectors, right, that are in both of those separate spaces, and these would just be coefficients of them. And most tensors are not pure, so that's kind of like just a better general tensor, or general tensor, right, notation. So let's tensor the real numbers in 2 dimensions and the real numbers 3 dimensions. What's their dimension? 3 times 2, 6, right? And then their basis would be described as such. We can describe isomorphisms. So if we take the vector space V and take the tensor of that with the scalar field, it's isomorphic to V. So and that's kind of an interesting fact, right? Because we take the tensor product between V and lambda. And remember, lambda is just a scalar, right? So it's a scalar field. So just scalar times the vectors, right? If we take the direct sum of vector and a subspace of the vector, okay, or it doesn't have to be a subspace of the vector, it could just be any vector space, and then take the tensor of that, then you could just canonically represent them as the direct sum of V tensor with W and U tensor with W canonically. And we can also describe that the dual space of the vector tensored with the just the W vector space, that's isomorphic. Isomorphic to the homomorphisms of V comma W. That just means linear maps from V to W. Anything that maps V to W. Again, we'll cover this at the end with category theory, but just think about this as structurally preserving linear maps from V to W, right? So a tensor, okay, interpretation. A tensor, again, right? It's phi tensored with W, acts on a vector as a function, right, of this map from V, right? Tensor of is a function of V, right, with the phi scalar, right, the functional V, with W or times W. So, and this would be the scalar, I guess, in front of the new vector W. So, the evaluation map, EV, right? That's the evaluation map, whatever. So, you're gonna see that if we take the dual space, or if we tensor the dual space with the vector space itself, onto the field, right? We take this map. The measurement, the function or the linear maps, right, tensored with the vectors, should give us just essentially it should just ascend linearly to all tensors. So it's a non-degenerate. It's also non-degenerate in finite dimensions. It's also symmetric and alternating maps. So a symmetric map would look like this, and an alternation map would look something like this. With that's the sine function. So becomes negative or positive 1 after some sigma. Becoming 0 or greater than 0, less than 0, whatever, right? So that's kind of another thing to keep in mind. So you can have symmetric and alternating maps. Cool. Now, again, in physics, right? Again, physics comes back. You can't separate physics from math. We often care about a specific type of interaction, which is called the antisymmetry. Okay? And fermions, essentially electrons, neutrinos, quarks, they can't occupy the same state. All right? This is the reason why they can't occupy the same state is simply because magnetic flux depends on orientation. It's signed, right? If there's something flowing into some space, right, then it would be, I guess, like positive, right? And if it's flowing out, then it'd be negative, it doesn't really matter what you choose for negative or positive, right? It's just the flux depends on orientation. Volume is signed, right? So to capture this, we actually need to restrict our tensors to something called the exterior algebra using what we call the wedge product. All right. And so the wedge product captures something called the geometry of exclusion. Okay. And what this means is if you try to wedge a vector with itself, right? So attempt to wedge, a vector with itself, then you're going to get 0. And this encodes the idea that you can't span, a parallelogram with only one vector. All right, so let's look at this. So again, exterior algebra, it's just a quotient of the tensor algebra. Again, so let's say we have a tensor algebra of the vector space, which is equal to the direct sum over k is greater than 0 of, v to the tensor sub k, or tensor k, where we let v tensor v, again, be equal to 0. And that product is denoted the wedge product, right? It's got to be equal to 0. The image of our exterior algebra is denoted as lambda to the k of v, all right? And the induced product on the exterior algebra is the wedge product with the alternating map, okay? And the properties of this are, we have anti-commutativity, which is formulaically given as this, and associativity, which just means that we can kind of do the same associative operations that we've been doing since elementary school on them. But the structure of the exterior algebra looks like this. So if we choose some basis, right, for the vector space, and we choose a basis for the exterior, or we want to choose a basis for the exterior algebra of the vector space, it'll consist of just wedges, right, with increasing indices, right, where we have I of k, right? Okay, if that makes sense. So here the basis would just be En, right, E sub n, but here it's E sub I sub k, all right? So the dimension here would be n choose k, all right, depending on what we choose for the quotient of the tensor algebra, okay? So let's look at n equals 3. The basis here would be E1, E2, E3, but if we look at the exterior algebra for the tensor spanned by E sub I, again, that's what this looks like. But if we have it to be equal to 2, it'll be E wedge E1, E wedge E2, E1, E wedge E3, E2 wedge E3. And the exterior algebra for here will be E1 wedge E2 wedge E3. And it's in choose K. All right. So as we choose different, as we quotient it by this chosen the chosen K, right? Our choices for K, then we will get different exterior. The exterior algebra will define our bases, all right, in terms of our wedges. Now let's look at the determinant. Why do we do all this, right? What's the point? Why do we need to define an exterior algebra? Like, it just looks kind of like, like it's not really clear. Well, it turns out that because a wedge product captures that geometry of exclusion, and because it encodes this. First of all, this encodes the very deep idea you can't span a parallelogram with only one vector, right? There's no way to do that. There's no way to traverse an entire volume, an area, right, with one single vector. So this gives us a coordinate-free definition of the determinant. So that top exterior power, right, that we're talking about, if the top exterior power of a space is one-dimensional, that represents volume. Any operator acts on this line here, right? Any operator that acts on this line by a single scalar, that scalar is a determinant. Hopefully that makes sense. It's not a formula involving diagonals. It is literally the volume scaling factor. Okay? So, let's walk through this. All right, so if we have an exterior power, the top exterior power, as dimension, in choose n, And again, because that space is one-dimensional, the map must be multiplication by a scalar, and the scalar is the determinant. And of course, this volume, right, is a volume map, but allows us to take the determinant and be able to create, to just find something called a volume form. And the volume form would just be a non-zero wedge product. Okay. And then let's do a computation. So let's say we have let's have a tensor that has a matrix A and a basis E sub I. Then a determinant A is a coefficient. I'm sorry, not a tensor. It should be a linear operator. Sorry, any linear operator that induces this map is the coefficient such that we have the operator as a function of all these series of wedge products. This will just be equal to the determinant of the matrix A and the basis of E sub in, right? Okay. Why? Okay, still, like, we have these volume forms, but, like, who cares? What does it have to? What does this have? We have a nice way to scale volumes, whatever. Well, guess what? We can apply this directly to the geometry of motion itself. Okay, this is what we call symplectic geometry, or the geometry of phase space. Now, if you've studied physics at all, you understand that phase space, any trajectory in phase space encodes a solution to Hamilton's equations, or first order differential equations that are coupled to describe reality, essentially. Now, if you don't know that, that's okay. Just think about this like this. In standard geometry, we'll measure lengths using dot products, right? But in Hamiltonian mechanics, we measure areas, right, flux, and this requires a new type of geometry. So we're going to define something called a symplectic form, omega, on a vector space V that is real and finite dimensional. And it is a form that is first and foremost bilinear. Okay, depends on two variables in general. And if you could guess what those two variables are, it's position and momentum. Okay. But let's talk about this in a general sense. In Hamiltonian mechanics, the physics of phase space really is, we don't care about length, right? We care about area. And phase space comes in pairs, right? Position, momentum. And, this is a machine that will take two vectors, right, and compute a signed area between them. So that's what the skew symmetric means, right? So, and also non-degeneracy. This non-degeneracy just means that it requires a vector space to be even dimensional, okay? Given that we have, V and W, right? Now, the structure allows us to do something very magical. It allows us to derive Hamilton's equations purely from geometry, all right? And you will see this very, 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 very deep connection if you've never seen this before. Now that we have properly defined what multilinear algebra is and exterior products or wedge products, let's look at the phase space, let's look at the vector space, which will be, again, non-degenerate, so it's r to the 2n, with some coordinates, again, right? So we need to have coordinates and momentums matching for those particular, for this particular system. And, we then have the symplectic form, which is, again, just going to be the sum of all the generalized coordinates that we're choosing to use in generalized momentum. But we're going to define it as a wedge product between both of these. And this symplectic form is the sum of just all the wedge products, basically. All right? And these are what we call dual basis elements. So we explicitly show this. We have that the symplectic form is a function of q comma p and q prime comma p prime. Looks like this. And you can even actually represent this as a matrix as well, which is just 0, 0, identity, negative identity. All right. So these are identity matrices. Okay, so a matrix inside of a matrix. We can look at the linear Dorbeau theorem. And what this looks like is if we have every symplectic vector space emits a canonical basis or a Darboux basis. Okay, so this is another mathematical kind of finding we can use. So let's say we have E1 to En and then F1 to Fn, such that here's our our symplectic form of if the indices between EI and Fj are there, then we have the Kronecker delta. Okay, so means for f of I and e of I together, we define that symplectic form would be 1, right, for a canonical. We're just defining the bases, remember. And then E1 and EJ, 0, Fi and Fj, 0, okay? And that's great. So you can try to prove this. Just choose some non-zero vector. Some non-zero vectors that you put into the symplectic forms, and then they're not equal to 0. Rescale them to be equal to 1. You can show this, okay? And prove by induction. Let's compute R4, okay? Let a symplectic form be the sum of these two exterior products. So say, I don't know, we have, I guess, two particles, whatever. And the basis would look something like this, where we have the derivative of or the operators, right? That are just they're showing us the change in the coordinates and change in the momentums. Or we can even take just the duals, okay? So this is our basis, but we can take the dual of that and just say dq1, dq2, dp1, dp2, all right? Then the symplectic form of this is just the Kronecker delta, okay? So really, really simple. I mean, very nice. Now that we have this mechanics here, let's show what Hamiltonian mechanics really is, okay? It's not just a set of equations. It is an intrinsic geometry of symplectic spaces. So, okay, given a function, all right, energy, usually we think of the gradient of energy as like a vector pointing uphill, right? But in phase space, motion doesn't go uphill. It flows along, again, those level sets or those contours of constant energy, right? So we can turn the change in energy, really, the symplectic form, omega, right? It twists the gradient and it takes the uphill direction, right? And it rotates it 90 degrees in the abstract phase space and turns the change in energy into velocity. And this one equation here, well, technically, I guess, two, but I mean, this is a more abstract version of it. This says it all. It says that the symplectic form here eats the velocity vector, right? This symplectic form will eat the velocity vector and will spit out the negative gradient of energy. And this just generates the flow of the entire universe. All right? So that's what that essentially means. Okay? And just like the determinate measured volume, right, we can then arrive at the Liouville theorem, Liouville measure. But let's first derive Hamilton's equations from this, okay? Just to show you that it works. Let the Hamiltonian of Q and P be the energy. Let the vector field be the sum of the coordinates and the coordinate operator and the momentum operator. Compute the symplectic form. All right. And using the definition of the symplectic form, we can then get Q to the J or Q super J out of it. Remember being precise with our dual vectors and our bilinear forms or bilinear space. this must be equal, right? So if we do a sign check, we can get, again, the mapping that we want and derive the negative. Again, we can derive the gradient of energy, or the negative gradient of energy, and get the result of Hamilton's equations. All right? So it's encoded within the geometry itself. It's encoded within this bilinear, pretty much tensor algebra that we've created. Okay? It's a very nice application of multilinear spaces. Okay? Now, if we look at harmonic oscillators, I'm not going to go through the whole thing if you want to look at this, but essentially we get the standard result that you normally get in a regular mechanics class for harmonic oscillators that are together, okay? Poisson brackets, okay? What is a Poisson bracket? So it is the algebra, essentially, of observables. So let's say we want to calculate the Poisson bracket of f and g. It is equal to the symplectic form of the vector field of f and the vector field of, comma, with the vector field of g, which will just be the vector field of f acting on g, which is equal to the negative of the vector field of g acting on f. And at our both basis, we can construct, again, the Poisson brackets for these. And, again, the proof is involved, but you can essentially just say that the vector field for the coordinates is defined by the symplectic form, which is equal to the negative of our basis, right? Okay, or sorry, of our dual space. So if we can then just say that this implies that the symplectic form of x and given our operator d by dp sub j, or d momentum sub j, would just be the Kronecker delta, which implies then that the field is equal to the operator del p to the I, okay? So then the Poisson bracket can then be just equivalent to the Kronecker delta, okay? The Liouville measure, this tells us that this flow will behave very nicely like an incompressible fluid. And again, if this just sounds like physics gibberish to you, that basically means that all the information in this phase space can be twisted, stretched, scrambled, but it can't be destroyed. And again, what does this give us? Symplectic geometry gives us that volume, in general, is invariant, okay? Is an invariant under Hamiltonian flow. All right. And we can look at computations, again, for, n equals 1, and just show this for our volume forms. The volume form is just equal to dp, dq, exterior, product with dp, and the flow will preserve the area. So in general, with Liouville's theorem, the phase space volume is preserved. There's something called musical isomorphisms as well. Non-degenerate form allows us to map vectors to dual vectors by raising and lowering indices. All right. So the flat map just allows us to map the vector space onto the dual vector space with V, then mapping onto the symplectic form. And again, this is like our bilinear space that we're given. Our bilinear map, right? So it takes, again, two vector fields. But this would allow us to lower the index, right? Because it's a function of, we're getting our dual space, or we're mapping our space, our vector space to the dual space, and transforming that into our symplectic form. The musical isomorphism to get back, right? So we're pushing forward kind of ish, but it's a function of the bilinear form. Well, we can also pull back, right? Instead of pushing forward, we can also pull back from the lowering indice, or this would, I guess, raise the index of the space, right? And this would actually give us the inverse of the symplectic form. But we go from the dual space to the regular vector space. Given some symplectic form omega, the flat map, right? V mapping to the dual space is essentially just a mapping of V onto the symplectic form here, and then if it's non-degenerate, that implies that it's invertible. So that means that non-degenerate means determinant is not zero, right? Because the volume can't be, the volume form is invariant. So essentially the sharp would be the inverse of the flat, right? They're inverse to each other, and you can just raise and lower indices in phase space. In Riemannian geometry, the metric G does this, but in symplectic geometry, omega does this, but with a little bit of a twist, and this is called, again, skew symmetry. Now let's briefly glimpse at something called Clifford algebras. Clifford algebras allow us to define a product space where we have a tensor product between two vectors, and of course they are the same vectors, that's why they're V. But Q here is a bilinear form, and we're interested in the case where instead of defining an exterior product or a wedge product, we want the bilinear form times 1 instead of 0. This allows us to get a Clifford algebra, and this is the seed of something we call spinors, okay, that are used extensively in the Dirac equation, which is quantum field theory. You don't have to know this if you're not a physics guy, but you've probably heard of this guy's name before and probably heard of antiparticles or whatever. All right, so this is the seed of spinors, and we'll truly give them a good treatment in the physics chapter, okay? But the Clifford algebra, which takes in a vector space and also takes in a bilinear form, it quotients the tensor algebra, again, by the tensor product between both of them, right? Because what is a tensor product, right? We have two vector spaces that we want to map in linearly, all right? So we take the product of two vector spaces and map them in a linear way. And so we like mix them or do whatever. And Q is a bilinear form. You can use for the Dirac equation, the bilinear form is Minkowski, all right? So the Minkowski inner product, it's not super hard. So again, everything's very naturally kind of motivated. We really have a machinery now for interaction, right? We have we have tensors that combine vectors and symplectic forms to drive mechanics. But we're also assuming that our symmetries are static. So the next section, we're going to let our symmetries move, okay? And we're going to enter the world of Lie groups and transformations that are described continuously, right? All right, so we've built the algebra of vectors, the geometry of phase space, but our universe is not static, right? It moves, and it spins, it flows, it does all kinds of stuff, right? Physical laws are defined by symmetries, okay? So continuous symmetries symmetries are rarely discrete, right? Like jagged jumps, like rotating a square 90 degrees or whatever, right? Nature usually prefers smooth, continuous transformations. So a particle, right, can rotate by any angle, and a spaceship can just boost itself to any velocity, right? So to describe this, we need a structure that can be two things at once, right? It must be a group, right? So we can combine two actions, right? But it also needs to be a smooth manifold. In other words, we need to be able to differentiate them, right? The structure is called a Lie group, okay? And the miracle of Lie theory is the idea of linearization. So we're still kind of linearizing everything. By marrying algebra and topology. We the fundamental insight of Sophist Lee was this. It was that studying the whole curved finite group is extremely hard, right? The group of all possible rotations is a very like complicated, twisted shape, right? So just what we have to do is zoom in infinitely close to the identity element, right? The do nothing action, right? So like example, like I'm not gonna twist anything. I'm just in the same way like how you Taylor expand, right? Or you say like here's something at a point like, you know, I'm gonna look infinitesimally close to whatever, right? And I know we didn't really like the notion of infinitesimals, right? But we're gonna it's useful. It's a useful kind of fiction that we have the logical means of constructing a continuum. Now we can act as if we can use the fallacies and in a rough way, okay? But what this allows us to do is look at an infinitely close, you know, close to the identity element where we do absolutely nothing, don't transform anything, and the group itself will look flat. What that means is that the tangent space of the Lie group is the Lie algebra. And the Lie algebra is the linearization of the group. It describes the infinitesimal generators of the symmetry. So first of all, the group is essentially the rotation, right, of the planet, right, of some Earth, right? We have an Earth or a robot arm, right? We're going to rotate the thing. And the algebra describes the angular velocity vector. Okay, that's how you think about it. All right, but if you have a physics background, it's like, oh, really? That makes so much sense, right? Why didn't they just say that in math class? Okay, so essentially that's how this works. All right, so the Lie group or the manifold, right? It's a smooth manifold. It's also a group, right? Such that the group operations are smooth maps. So multiplication, if we take the product of the group, it maps to the group itself. So G comma H, might keep clicking on this thing, but G comma H just maps to G and acting on H, right? And we can invert the group, right? The group, if we, again, this is like a little endomorphism, but the element G will map to its inverse, right? So this is possible. There are submanifolds of the space of matrices. So we're just taking, here's the space of all matrices, right? Whatever, of n-dimensional matrices, abstractly. It's isomorphic to real numbers in squared dimensions, right? Because, I mean, what is matrix? It's just, you know, columns, right, and rows, and if they're square matrices, you know, you can square it, right? So if we take the general linear group, right? So these would be invertible matrices with determinant not equal to 0. This is an open set and it's not compact. Okay, now that we have the topological language from last time. The special linear groups are volume preserving matrices. Interesting. Volume preserving. Symplectic geometry. This is a hypersurface in the general linear group. All right. Orthogonal. These are orthogonal. The orthogonal group is distance preserving. So if we take the transpose of these, you know, matrices that are elements of this group, and the matrix itself, it becomes the identity. Okay, so it preserves distance. The special orthogonal, they're just rotations, right? And so they still are distance preserving, but they also rotate and they have determinant 1, and they are actually topologically connected spaces. Okay? If we look at the unitary groups, these are complex distance preserving, so they are self-adjoint, right? Or they're unitary. And there's a special unitary where they are complex, so they preserve the magnitude of a complex vector, right? We can move it around in complex space. And if they're unitary, that means that they're just determinant 1. Okay, so I'm sorry, special unitary. And then symplectic group preserves phase space volume. Okay, so a little bit different than the volume preserving matrices. This is real space in general, right? It's hypersurface in the general linear groups. But if we look at phase space volume, we have essentially that it'll preserve some symplectic form, right? So there's some other groups. There's a Heisenberg group. It's an upper triangular 3x3 matrices with 1s on the diagonal. Yeah. Poincare group. This is a semi-direct product of Lorentz group and transformations. Yeah, I mean, you want to learn more about them, look it up. Okay, the most important probably group for physics is the Lorentz group. And these are matrices lambda that satisfy that the transpose of the Lorentz matrices acting on some eta, where eta has a diagonals of, it's a matrix with diagonals 1, then -1, -1, -1. This is something called the Minkowski metric, all right? And it just satisfies this, okay? Satisfies this relation. So a lot like the symplectic group acting on the symplectic form, but instead we're just looking at this metric here. Okay, remember the metric, as we discussed previously, the metric is what gets preserved, but in symplectic geometry or in Hamiltonian phase space, the symplectic form gets preserved. All right. It has 4 components separated by time reversal and parity. Okay, and the component containing the identity is the proper orthochronous Lorentz group. And basically, they're just like special orthogonal matrices that are, it contains the identity and it's connected by time reversal and parity. That's what they call it, orthochronous, right? So, and they're proper, right? So, parity. All right, that's where it comes from. Okay. But again, let's go through the Lie algebra, right? So this is the tangent space of the group. So remember, the group is like the full rotation of some object, right? And the algebra is essentially the tangent space, or the angular velocity, if you will. So to do calculus on the group, we look at a tangent space at the identity element E. So the Lie algebra is usually denoted by some script G of a Lie group. G is a tangent space of at the identity. So let's say the Lie algebra is defined as this tangent space, or this operation, or the infinitesimal generator acting on the group with the identity element. Okay, this will make more sense in a minute, but how do we capture the group structure in this flat space? We will essentially, we will need to do some, okay, so when we flatten the group, right, into this space, the matrix multiplication is non-commutative. So basically that means A times B is not B times A. So when we differentiate this non-commutativity, we need to find something called the Lie bracket, all right? Or in quantum mechanics, it's called the commutator, right? So the commutator is just xy minus yx. And of course, there's an abstract definition for this. So you would say that, of course, the bracket is the Lie bracket of the left invariant vector fields generated by the elements of G of X and Y, okay? Left invariant vector fields means that if we do a left translation, that means if we do G acting on H, right, this defines left invariant vector fields, okay? And the bracket is the commutator of the corresponding left invariant vector fields, okay? If we look at one-parameter subgroups, one-parameter subgroups are smooth homomorphisms, okay? So that just means we're taking the real numbers, mapping them to the group, with gamma at 0 being the identity, okay? And the velocity, gamma, the initial velocity, is, x that belongs to the Lie algebra. This generates a subgroup gamma of t. So we're just parameterizing gamma of t as the exponentiation through time of this velocity field, okay? That is a member of the group itself, or the tangent space of the group. So the algebra, okay? The algebra is the tangent space of the group. So let's look at the algebra of the rotation SO3. This contains matrices of R with R transpose and R to be identity. Remember, because special orthogonal is preserving the distance in three-dimensional space, okay? And of course, it has determinative 1. Differentiate the identity. So if we take the derivative of these matrices, we can get the identity and then the vector field. And you can kind of evaluate those derivatives at t equals 0. And you'll get that the algebra of the Lie algebra of the rotation consists of skew symmetric matrices, and you can find them as this. Guess what? These are your angular rotation matrices, okay, or your angular momentum matrices. And they anti-commute, right? And so this is exactly the cross product algebra of the angular momentum vectors, matching quantum mechanics here. Opposite factors, right? The IH bar, but I mean essentially the same thing, right? So now you see where quantum mechanics comes from. So if we look at a general form, right? Let's say X is the vector field of X is just described by this, in general, corresponding to an angular velocity vector. Then the Lie bracket corresponds to the cross product of the vectors. So it's pretty. I mean, look at this, right? Because these are your bases, right? Here's your angular velocity vector, and they're acyclic, and they do that, and then, I mean, the form's all there, right? So essentially, the Lie algebra is generated by the rotation gives you quantum mechanics. All right, so that's just to put it simply, and you can search more, work through your own practice problems, etc. But yeah, the algebra is derived from the group. Again, that's probably the most important thing to understand. This bracket really also measures the failure. Really, again, it measures the failure of these symmetries to commute, right? So if you rotate, around the x-axis and the y-axis, you'll end up in a different spot, right? Than if you did in the reverse. So that's why the Lie bracket captures that idea, okay? And that difference is exactly captured. It's the algebraic kind of DNA of the symmetry. But how do you go from the algebra back to the group, right? How do we get from this flat kind of local map, right, to the global curved reality? Well, we use something called an exponential map. And we kind of talked about this a little bit, but in calculus, e to the x is a function. But in Lie theory, the exponential map is a machine, right? You feed it a direction in the algebra, a generator, right? And it shoots out a geodesic essentially. That's what's happening here. And a geodesic is just kind of a smooth path, right? That wraps around the group itself. It'll turn a straight line in the algebra into a circle or a hyperbola or whatever into the in the group, right? So when you're solving this differential equation, right? Here's the path that you're trying to get. There's your x, and then of course your exponential map is you get the algebra that maps to the group, defined as this, and the one parameter subgroup, the initial velocity x is this, and for matrix groups you can use the literal exponential, matrix exponential. And this is important, the Baker-Campbell-Hauser formula, multiplication in the group, corresponds to bracket operations in the algebra. So if you take the logarithm of the exponential maps of x and y, you can then just get x plus y, right, plus 1/2 of x comma y plus 1/12 of x comma commutator of x plus y minus 1/2 of y. So you get this whole kind of thing, but the first three terms, all right, are x plus y plus 1/2 x comma y. And the Trotter approximation tells you that, well, the exponential map with respect to time, right? We're trying to parameterize the time so that we can get the geodesic from the algebra onto the group, right? It's the limit, as in goes to infinity, of this guy. And if you know the commutators, you know the group multiplication near the identity. Okay? The adjoint representation means that if the group acts on itself by conjugation, you can get G to map between, you know, some other operators, H, G, and H inverse. And if you differentiate this action at the identity, you'll get the adjoint action of the group on its own algebra. So for example, the conjunction map says that if we have C sub G of H, right, we can take the generators, right, and you know, do this, we can fudge this H in between the generators, assuming there's an inverse to the generator, and differentiate it E, okay? So if we have the adjoint of G, this should be equal to the differential of the conjunction map, right, at the identity. And this is defined, or this DCG at the identity is defined as, again, an endomorphism of the Lie algebra onto the Lie algebra. And it kind of, it rings a bell, right, that we have, since we have a background in linear algebra, we know that, well, the adjoint acting on the x, right, on, you can think about this almost as like a way to look at different bases, right, and map like the initial basis to the change basis, the transform basis. There's a way to map between them, you know, with this adjoint action on the group in its own algebra, okay? And so that's kind of the matrix case where we have the generators acting on the field and then the inverse generator. That'll give us the adjoint or the conjunction map, okay? So the differential, the little adjoint, right? So we can take the differential of this adjunction representation, which just means that we have the algebra mapping to the endomorphism of the Lie algebra, okay, and the little add of the vector field x, then we can put it on y. Guess what? That's equal to the commutator, okay? So the Jacobi identity in the Lie algebra is equivalent to add preserving the bracket. And if we want to compute this out, there you go. We can take the add of the exponential map times the inverse of the add, and we'll get the exponential map itself, okay, of the add acting on the field, okay, of the add of the Lie algebra, or sorry, the generator, okay. So that's cool. And to prove that, you would conjugate the one parameter subgroup. We can also define an inner product in the algebra using only the bracket structure, and this is called the killing form So the Killing form is just, b comma y, which would be equal to the trace of the little ad, right, or the differential of the adjoint representation, right? Sorry, I lost my place. Composed with the little ad of y. Okay. So again, the Killing form is the trace of the little ad of x composed with the little ad of y. And Cartan's criterion says that a Lie algebra is said to be semi-simple, which means it's a nice decomposable into simple little blocks like Lego, if and only if the Killing form is non-degenerate. Okay, so it cannot be degenerate for us to be able to have the semi-simple Lie algebra. So if we want to compute the special unitary representation, we can look at the basis, or we can choose a basis for h, and e plus and e minus, right, up to 2 factors. Then the little ad of this e plus, right, would then be equal to 2 times 2e plus, and then the little ad of h, of the h basis acting on e minus, right? Because again, we're choosing a little ad based off of the basis that we chose, right? So I negative I, it would look like this, okay? And sorry, this would be for the little ad with the e plus basis, acting on e minus would give us h, etc., right? So again, we're tracing, the traces yield the Killing forms. They're non-degenerate, so they're semi-simple. And for physics, right, for compact groups like SU2, or special unitary groups, which preserve what? They preserve complex distance, right? The Killing form is negative definite. So that means that the standard metric for gauge theories, like Maxwell's field strength tensors or the electromagnetism, this is used for or SU2 describes the transformation laws in the algebra in terms of negative definite Killing forms. So that's kind of we'll get into that in chapter 4. We have a long way until that, like maybe like a couple more hours, but that's essentially what we're building up to. All right, so group actions and homogeneous spaces. So we'll say a smooth action with G, the group, the product of the group, and some M, right? And we're mapping this onto M, right, on a homogeneous space. So what this looks like is we have our generators, right, for G and P to map to G times P. Okay, our momentum. Or P in general, it just can be anything, right? But the orbit will look like G times the momentum, or some parameter, right, that we're trying to describe the orbit. So the group itself just describes that entire trajectory along that group action, right? And the stabilizer of the let's just say momentum, okay? The stabilizer of that momentum, or of that coordinate, right, is going to be defined as the generator, given that the generator acting on the momentum is equal to the momentum, okay? The orbit stabilizer theorem says that if we have some group acting on the momentum, that means that the group quotiented, or that means it's isomorphic to the group quotiented by the stabilizer of the momentum as manifolds if the action is free and proper. So for example, right, let's say we have the special orthogonal matrices for SO3, and they act on the sphere, okay? Orbits will then be latitudes, right? So you can think about, except poles, right? Because poles don't have any orbits, right? It's just a point, right? But the orbits themselves will be SO3 quotiented by SO2. And another cool example is the Grassmannian, which is GR of K comma N. And this is a space of K planes in the real numbers and in dimensions, which is isomorphic to the general linear group of n, quotiented by the general linear group of k, and of course, in parentheses, general linear group of k with a product of the general linear group of n minus k. So this is a Grassmannian group as well, okay? That help us understand group actions on just homogeneous spaces, right? The momentum map then allows us to connect symplectic geometry with this section here. And this is when everybody talks about like Noether's theorem, right? Continuous symmetry implies conservation or whatever. This is exactly the kind of deep level of rigor that you need to fully understand Noether's theorem. You don't really understand Noether's theorem. And again, this is the subject of this entire video is invariance, right? But you don't fully understand it until you've walked through the Lie algebra and Lie groups and some symplectic geometry as well, okay? So we already saw, right, symplectic geometry links energy to motion, but now we link symmetry to conservation. And if a Lie group acts on a phase space, again, we're just applying Lie groups to phase space. Every infinitesimal generator of the algebra corresponds to a specific function on the manifold. So, for example, right, if the symmetry is a translation, okay, its conserved function is momentum, right? If the symmetry is time translation, then its conserved function is energy. If the symmetry is a rotation, its conserved function is angular momentum, right? We don't need to derive all of these laws separately, right? And we can show, remember, we're just saying let G act on symplectic's phase space, preserving omega, which is, we'll just call a funny word, it's called symplectomorphism, okay? So for every vector, right, that's in the infinitesimal generator, right, for any vector that's in the Lie algebra, which is a infinitesimal generator, there's a field, or there's a vector field on the phase space, okay, that we're parameterizing in terms of the exponential map. Well, if the action is Hamiltonian, there exists a function, J, which maps a vector space, a symplectic vector space, onto the add-valued Lie algebra, right, the adjoint Lie algebra, valued in the dual of the algebra, such that we have, again, J of V, and we have our linear map acting on our the element of the vector in that generator, and we get H. So just defining this as this form into H, where H is the Hamiltonian function generating the flow of that vector field. All right. Well, guess what we get? So if we take again the negative gradient of the Hamiltonian in terms of the symplectic form, we then get equivariance. So the equivariance tells us that this particular function that we defined, valued in the dual of the algebra, right, where we have G dotted with V, is equal to the adjoint representation of the algebra, the inverse of the Lie action, okay, with that map itself. So what that basically means is the equivariance that's defined here, we get a conservation that along any Hamiltonian flow, right, where we're parameterizing it in terms of the geodesic that it generates, right, from this momentum map. We're calling this a momentum map, right? Along any Hamiltonian flow, we get that the time derivative of it is 0. And what this means then is that you can basically have a geometric object that translates the abstract symmetries of the Lie algebra into concrete conserved quantities of physics. It's essentially what we've generated here. So the conserved quantity associated with the rotation symmetry is the angular momentum vector L. And you can show this first, just defining the group as the SO3 rotation. The generator is the rotation axis. The vector field, again, depends on the coordinates and the momentum. And then the Hamiltonian, of course, we can define as this, and then the momentum map is given as such, right? It's just Q cross P. So we can also show co-adjoint orbits. So the momentum map will land in the add-valued Lie algebra, and the group acts on G star via the co-adjoint action. So we can compose. Let's say we have the adjoint representation of the algebra starred acting on mu. Well, we can also do mu compose with the inverse of that algebra as well for here. All right, and that will also give us co-adjoint orbits in terms of the actual. Essentially, you can just go back from the adjoint to the actual group action itself. Okay, so there's an interesting theorem that says that every co-adjoint orbit is naturally a symplectic manifold. So essentially, because we have that symmetry conservation, we can then go back to the symplectic manifold from our conservation laws, which is very nice. So for SU2, co-adjoint orbits are spheres. These correspond to classical spin systems, spin J representations, right? In terms of the quantum numbers for spin, right? Boom, there you go. All the physics for you. So let's classify everything and highlight what mathematicians have successfully done with simple Lie algebras over the complex plane. So we have the special linear group of n+1. This is volume preserving. We have the special orthogonal groups for n2 plus 1. These are rotations in odd dimensions. And then we have the symplectic groups for 2n. And then we also have special orthogonal groups of 2n. These are rotations in even dimensions. Okay. There are some exceptionals. There's some groups here that are some monster symmetries that are invoked in string theory. So not only do we have these groups, there's also some more exotic groups that exist as well, like E8, E7, E6. You know, like I think there's like a flavor of heterotic string theory or something, or E8. You know, just whatever, right? But I mean, people have messed around with these particular mathematical structures that, you know, because of Noether's theorem, right? And then of course, compact real forms. So we have, you know, special unitary groups of n, and then special orthogonal of n, you know, symplectic form of n. Interesting ideas. And then the last thing that we're going to talk about is representations. So we'll talk about this later in the next video, but finite dimensional representations of connected Lie groups correspond via differentiation to representations of the Lie algebra. So for compact groups, every element in the image of the exponential map are unitary representations. All right, so that's kind of what we'll then discuss representation theory. But I mean, at the end of the day, right, we essentially have created a geometric object, again, that translates the exact abstract symmetries and invariance encrypted by the Lie algebra into this concrete conserved quantity, or concrete conserved quantities of physics. And that's really the most important thing to talk about. We've synthesized everything from vector spaces, operators, tensors, and symplectic forms and Lie groups. It's now complete. But we have a zoo of structures. I mean, we have vector spaces, dual spaces, manifolds, groups, algebras. It's getting really crowded, right? So we need a way to organize them. We really need a kind of a mathematics of mathematics, or a meta-mathematics, if you will. So welcome to category theory. All right. So we've reached the end of chapter 2, and let's look at what we've built so far in the video. We've amassed this entire zoo of structures, right? We have vector spaces that describe states. We have dual spaces that are for measurement, right? We have linear operators for changing things within the vector spaces, for dynamics, rotations, whatever. We have symplectic forms for phase space, and we also have Lie groups that preserve symmetries. But it's getting really crowded, right? What's happening is it's really messy, and we've defined these things in isolation, but in the real world, in real math, they interact. So groups on vector spaces, right? Manifolds have tangent spaces, which are vector spaces. So, and that's essentially what, the Lie group and the Lie algebra are, right? So we need a way to organize this, and we need essentially mathematics of mathematics, okay, or second order mathematics. And welcome, essentially, to category theory. This is often called abstract nonsense by mathematicians who haven't realized its power yet. But for us, this is a crucial shift in perspective. All right. So until now, we've defined objects by just, looking inside of them. Right. We ask, what is a vector? It's a list of numbers. Right. Or what is a group? It's a set of elements. Category theory just changes the question. It says, don't really look at the object, right? Look at the arrows. Look at the morphisms, right? So an object is defined not by what it is, but how it interacts with everything else. And this allows us to describe or to define a category. And a category is essentially going back to math, the chapter 0 that we initially had for the logic of mathematics, was the universe of discourse, right? And every time you have a universe of discourse, you can think, okay, well, we're doing second order things now, okay? Because we now have objects that we're defining objects, morphisms. So just two objects with a homomorphism of arrows that connects them. Composition. So these are like rules to combine arrows. So if we have objects, with arrows to other objects, and let's say G has B to go into C, then if we compose these arrows, we can just go from A to C, with G composed with F, all right? And the associativity would hold in the identity. So there exists some arrow, right? The identity of A that does nothing, okay? Now, what this allows us to do is describe, again, vector as a the vector category over some field, where the objects themselves in that universe are vector spaces. And the morphisms on the vector spaces are linear maps. Okay, there's groups, so the universe of all groups, topological spaces, the universe of all topological spaces, and in the group category, arrows are homomorphisms. In the top category, the arrows are continuous maps. Okay, so if you understand arrows, you understand structure. So, and you can compute this, right? So if we have the vector, or the category of vectors, in the real numbers, the morphism set between, V going on to W is just the vector space of linear maps with the composition of the usual function composition, okay? And so again, it's a structure preserving map, okay? Now let's talk about functors in terms of what they are. So essentially they should allow us to move between universes. We use a bridge between the universes that we call a functor, and the functor is a machine that translates one category into another. It takes objects, and crucially, it takes arrows as well, two arrows. Okay, so functors acting on objects, or functors can also act on arrows too, and it preserves composition and identities. A contravariant functor just reverses the direction of the arrows, so it allows us to change the arrow direction, basically. All right, and then a covariant functor just assigns to each object A in a category such that we define the morphism and preserve the identities. Okay, so covariant, contravariant. I would say really we've already used these things. So think about it. Dual space. So this is how we denote a dual space functor. um, it takes a vector space V and spits out a measurement space V star. It takes a map T and spits out a dual map T star, right? So that would be a dual space functor. There's also something called forgetful functors, which is right here. So let's say we want to create a functor that allows us to forget multiplication going from the group to a set, right? For group objects to a set. Or if we have vectors, going to an abelian group, which then goes to a set, right? These are all forgetful functors, okay? They forget that you can add vectors and treat them just as a raw set or something, And I didn't mention a free functor, but it's basically when you take a raw set, some raw set, and then you construct a vector space out of it, okay? That's a free functor. Now, what's important to understand is the idea of naturality. So we kind of dealt with this earlier, and naturality is really important for physics, right? Because it gives us a rigorous test, essentially, for what is physically real, right? So it becomes a mathematical test to decide, whether, like, my coordinate system in and of itself is, like, changing and, like, not respecting, like, reality. What I mean by that is mathematics. So, okay, first of all, let's say given two functors, right? And where we have an arrow that's connecting two categories. The natural transformation eta will assign to every object A an arrow such that for every arrow, the square commutes as such. So if I were to compose the functor on the F arrows with the eta sub A arrows, the eta sub B arrows should compose with the functor acting on, or with the other functor acting on F, okay? So in each eta sub A is an isomorphism, and eta then is a natural isomorphism, okay? Now let's go back to this. Why do we need this? And why does category explain, if you remember, we asked if a vector space V is the same as its dual. And remember, math told you, yeah, they're isomorphic. They're the same thing. They have the same dimension, right? Something has the same dimension. That's a nice invariant. That should, we're away from coordinates. It doesn't depend on the coordinates. We said, essentially, but this kind of feels wrong, right, to say, because, vector space going to its dual, like, it's completely different, right? And it depends really on the basis that we chose initially for that vector space to give us the dual. So category theory says the isomorphism between V and V star is unnatural. So to build it, you have to pick a basis, you have to make an arbitrary choice, and if you change your choice, the arrow moves. This is an artifact of your perspective, and inherently the choice of basis itself is not a law of nature. Okay? So it is, again, it gives us the specification that this isomorphism is unnatural. However, the isomorphism between V and its double dual, remember we said that is natural because the map, right, J sub V, requires no basis, and it requires no coordinate system, and it works identically for every object in the universe. In physics, we only care about natural transformations. If a law depends on your choice of basis, it's not a law. It's a mistake. Okay? Now, exact sequences. Or before we go to the exact sequences, let's talk about properties and adjunctions. So, this is one of the deepest concepts in mathematics because we say the free functor and the forgetful functor are adjoint, and they are opposites. One builds structure from nothing, and the other destroys structure into nothing. And they maintain a nice mathematical universe. Okay? So we can have, again, categories and properties. So you begin to describe objects by universal property, and that object 1 gives you homomorphism between A and 1. Then it has one element for every A, and it becomes a singleton in a set. The initial object, or the dual, is the empty set in the category of sets. Okay? So we're able to generate the idea of objects from categories themselves. Alright? The product again, is not defined as ordered pairs anymore. The product now is defined as a unique object that maps into A and B, such that any other object mapping into A and B factors through it. Okay, and that there's universal maps for both. This gives us projections. All right. Now, coproducts become universal maps out of both things. Adjunctions then tell us two functors are adjoint if it maps out of the functor acting on the object, and if that corresponds if the bijectively maps into the category, or sorry, into the functor G acting on B. An adjunction then between two functors consists of a natural bijection here, where we have the homomorphisms on the D category, right, with a functor and their homomorphism with the object B, and that they're isomorph. That this inherently is isomorphic between the category, or sorry, the homomorphism on the category C for A, comma the functor acting on B. Okay, with the G arrow. Okay. Now this gives us again the free functor and the forgetful functor to essentially take the set S and make a vector space with basis S, and then this will just forget the algebra, okay, for G to and F. And the adjunction then allows us to define a map where, from a free vector space, this is exactly the same as defining a function from its basis set. Okay, if we look at a free modulo functor, so we, from the set we create from the set we define the functor from the category of sets to the category of the module over R. We can send some set S to a formal R linear combination, and this is left adjoint to the forgetful functor, okay, where we just map it back onto to the set. And then, of course, this also works for like bilinear forms as well. This corresponds uniquely to linear, right? So we take the bilinear map, right, to the linear map using the tensor product between these two spaces to create the new vector space that is a fundamental object on its own. All right. The Yoneda embedding, the functor Yoneda allows us to take a category and take the functor of the category and map some objects into the essentially define faithful homomorphisms, and embeds the C into the category of something called presheaves. Okay, so an object is completely determined by the morphisms into it. Okay, so that's more philosophical. We will come back to this, but I just wanted to put this out here. Abelian categories. What this allows us to do is, let's say we have the category of vectors and categories, or just of abelian groups. We have these ideas of kernels and co-kernels come back, and we can use something called exact sequences. All right, so assume that an abelian category has a zero object, it has biproducts, it has kernels and co-kernels for every morphism, and every morphism is a kernel, and every epimorphism is a co-kernel. We can then say that the category of vectors, category of abelian groups, and category of mod sub R are abelian. Okay. Exact sequences. We say the sequence is exact at B, right? Let's say the sequence would be exact at B. If the image, so the image of this first map here, is exactly equal to the kernel of the second map here. All right. So really think about that. What that means, right? The kernel is what gets destroyed. Remember, it's everything that maps to zero. The image is what arrives. And so if the image of the F arrows is equal to the kernel of the G arrows, that means everything arriving from A is precisely what gets destroyed when it tries to leave B. And this is a conservation law for structure. It tells us that if these objects fit together perfectly, there are no gaps and no overlap. So we can also construct sort exact sequences, which just implies then injectivity if the kernel is zero, P is surjective, the co-kernel is 0, and so the quotient of both of these objects is isomorphic to C. You see what I'm saying? So the quotient here of them is isomorphic to C. This means that B is a composite object glued together from A and C. All right, and then here's several examples. The integers modulo 2 are the co-kernel of the even integers inside the integers. Another example is cyclic extensions as well, all right, of the integers. We can look at diagram lemmas. So there's the 5 lemma and the snake lemma govern commutative diagrams with exact rows. So here's an exact row, here's an exact row, and we're saying that there exists a sequence, right, where we can make a connecting map between the kernels of these arrows here and the co-kernels of the arrows, all right? And they're constructed by something called chasing, okay? When we create a chasing map, this allows us to lift the element in the kernel of gamma to B and apply beta image in the kernel of the co-kernel map and descent. So a tool for chasing diagrams is if you have a map between two short exact sequences, the snake lemma produces a long exact sequence of kernels and co-kernels. All right, and this is really important for physics because this is the algebraic machinery behind cohomology, which we will use in chapter 3 to detect topological solitons, magnetic monopoles, or quantum anomalies. All of these things we describe in terms of cohomology. All right. When exactness fails, okay, so we have all of these things. If everything, we're assuming all of the image and the kernel, fit or whatever, but if they don't fit, if the image is smaller than the kernel, then that gap we are going to define as something called homology. Homology measures, again, the failure of exactness, or the measures the defect within the arrows that are mapping between the objects. So let's look at a sequence where d squared is equal to 0, and applying the map kills everything. It'll kill everything. So let's say we have some object Cn plus 1. We apply the map on Cn, and we apply it again. We get Cn minus 1 with d squared equals 0. And since d of d is 0, we know that the image of d to the n plus 1 is a subset of the kernel of d of n. All right. So this allows us then to describe homology groups. This group measures the holes or defects in the structure, and if the sequence were exact, h sub n, that would be 0. A chain map, F, allows us to take the object C and turn it into D and commute with differentials. Chain homology tells us that we have two chain maps, and the chains are homotopic if there are maps S sub n, where we have the object C sub n mapping onto the object D n plus 1, with the F minus G being defined by ds plus sd. All right, so this is what we call chain homology. Mapping cones allow us to do complex shifting on the object D and attach C via some arrows. Okay. If this isn't really, I'm just kind of, the chain complexes, we'll use them more mechanically in the next section, but I'm just kind of putting this out there to introduce them. So again, projective resolutions derive functors. So we can say a module P is projective if this is exact and if we lift against surjections. So every R module M has a projective resolution, and we can create something called derived functors. And the left derived of a covariant is the L sub n of the functor acting on M, and this is actually equal to the homology group of the functor acting on some projective resolution, where P0 or P dot is there's an error connecting P dot in itself. Okay. Now we then I'm going to skip this for now because we're going to use this, and I'm going to show how to. I'm going to explain this in a more intuitive way in the next episode. But projective resolutions derived functors means that essentially we can then use the properties of this projective resolution. Okay. And then again, from the snake lemma, we can construct from short exact sequence of chain complexes the long exact homology sequence. Okay, from the homology groups of those objects, with connecting some induced mapping. Okay, on the degree in part. So okay, what did we do in this? If this is going over your head, that's okay. But what did we do in linear algebra? Right, there was a difference between the dimension and rank, and the difference between, natural and unnatural, chosen bases, and even though the math was telling us that they're isomorphic because the dimension is the same, right? Homology, again, in category theory, homology measures the failure of exactness and the defect. Again, so in topology, this homology will give you the literal holes, right, in donuts and spheres where the geometry fails us to close up, or where it fails to close up. In quantum field theory, these algebraic holes will correspond to topological solitons, magnetic monopoles, again, anomalies. And homology really is the tool that we use to detect features that cannot be smoothed away, right? They are intrinsic to the objects that we are studying themselves and their morphisms, okay? So we're done. We're done with the algebra, okay? We've rebuilt mathematics without a grid. We have vector spaces to give us a stage. We have, spectral theory to give us invariance of motion or eigenvalues, right? We have tensors and symplectic geometry that gives us the physics of interactions and phase space. We have the Lie groups that elevate symmetry that allow us to construct continuous smooth symmetries, and categories then, and specifically homology gives us kind of a universal language to bind all of these crazy zoo of mathematical objects together, okay, in an organized way. So our structures are now perfect. They're invariant, they're coordinate free, exactly what we wanted. And now we have to deal with the fact that we're floating in a void, right? These are abstract kind of ghosts that are, mathematical constructs, but to do real physics or describe, gravity or fields or the curvature of the universe, we need to transport these algebraic engines that we've built into real, into a curved geometry and world. So I think we're ready now to begin to start bending space with math, all right? So, and curvature itself will then really give you a natural description of forces and physics, and connections will allow us to describe potentials. So again, but before we talk about that, we need to have the mathematical description of this. So in the next episode, we'll talk about manifolds. We're going to weave algebraic fibers, right, into manifolds by creating bundles, connections, curvatures, and gauge fields of modern physics. All right. So thank you for watching.